We have already learnt that the Rutherford's nuclear model of an atom basically suffers from major drawbacks, which are as follows. Firstly, it couldn't explain the stability of an atom in the view of the electromagnetic theory. Secondly, as a consequence of its inability to explain the stability of an atom, it couldn't explain the observed atomic spectra. This is because, according to the electromagnetic theory, an accelerated electron continuously emits energy, and ultimately it falls into the nucleus along a spiral path. As the electron is emitting the energy continuously, the spectra of such an atom also should be continuous. But the spectra of elements indicate that atoms emit energy discontinuously, and hence the Rutherford's atomic model couldn't explain the observed spectra of atoms. Another drawback is that it could not explain the electronic structure of atoms, that is, the distribution and energies of electrons in an atom. These drawbacks inspired several scientists to revisit the historical results about the behavior of electromagnetic radiation and its interaction with matter in order to improve the Rutherford's atomic model. The improvised outcome of the Rutherford's atomic model is the Bohr's atomic model. Bohr's theory could successfully explain the stability of an atom as well as the discontinuous spectra for hydrogen atom. To understand the Bohr's atomic model, it is necessary to first acquaint ourselves with the nature of electromagnetic radiations. The underlying principle behind the Bohr's atomic model is the quantization of energy, which is explained in the latter part of our discussion. Energy can be transmitted through space by electromagnetic radiations. These electromagnetic radiations are the best described in the terminology of waves. The wave nature of electromagnetic radiation was established in 1870 by James Clerk Maxwell. Let's now understand the general characteristics of waves. An object produces a series of waves when it vibrates continuously. However, the vibratory motion of charged particles, like electrons, produce a wave train of oscillating electrical field and magnetic field. Such waves, which are produced due to the periodic motion of charged particles, such as electrons, are called electromagnetic waves. This is suggested by James Maxwell. Note that the name electromagnetic radiations is attributed to the waves that consist of oscillating electrical and magnetic properties. An electromagnetic wave can be represented as shown. To characterize a wave, we need to specify its properties, such as wavelength, frequency, and wave number. A wavelength is the distance between two successive crests or troughs of a wave. Wavelength is denoted by the Greek letter lambda. It is expressed in either centimeters or meters or in angstrom units. The next characteristic of a wave is the frequency. Frequency is the number of waves that pass a given point in 1 second. It is denoted by the symbol nu and is expressed in hertz. Velocity of a wave is defined as the distance traveled by a wave in 1 second. Velocity is denoted by c and is expressed in centimeter per second. Let's now understand the relationship between the wavelength, frequency, and velocity of a wave. As frequency is the number of waves passing through a point per second, and wavelength is the length of each wave, their product will give the velocity of the wave. The electromagnetic waves travel through empty space with the velocity of light. The last characteristic of a wave is the wave number, which is defined as the number of wavelengths per unit length. It is denoted by the symbol nu bar and given by the equation nu bar equals 1 by lambda per centimeter. Now, let us solve a numerical problem on the basis of the characteristics of a wave. Calculate the wave number and frequency of violet radiation having wavelength 4000 angstrom. First, let us calculate the wave number. The first step involves writing the formula to calculate wave number, that is, nu bar equals 1 by lambda. The given lambda value is 4000 angstroms, which is equal to 4 multiplied by 10 raised to the power of -7 meters. The second step involves substituting the value of lambda in this equation. On solving, we get nu bar is equal to 2.5 multiplied by 10 raised to the power of 6 per meter, or 2.5 multiplied by 10 raised to the power of 4 per centimeter. Now, let us calculate the frequency of violet radiation. The first step involves writing the corresponding formula nu equals c divided by lambda. The second step involves substituting the value of lambda, that is, 4 multiplied by 10 raised to the power of -7 meters, and velocity of radiation, which is equal to 3 multiplied by 10 raised to the power of 8 meter per second in the above equation. On solving, finally we get 7.5 multiplied by 10 raised to the power of 14 per second. Now, let's look at certain key properties of electromagnetic waves. Electromagnetic radiation, as shown, is a form of energy that consists of alternating electrical and magnetic fields produced by oscillating charged particles, are perpendicular to each other and perpendicular to the direction of propagation of radiation. Unlike sound or water waves that require a medium for propagation, electromagnetic waves can move in vacuum at the velocity of light, that is, 3 into 10 raised to power 8 meters per second. All electromagnetic radiations travel with the same velocity but differ from one another in wavelength and therefore in frequency. Let us have a look at the arrangements of different electromagnetic radiations in increasing order of their wavelengths or in decreasing order of their frequencies. When these electromagnetic waves of different wavelengths are arranged in the order of increasing wavelength or decreasing frequencies, it is called electromagnetic spectrum. Of these, The radiations that are visible to the naked eye constitute the visible spectrum. The frequency range of the visible rays is 3.9 into 10 to the power 14 to 7.9 into 10 to the power 14 Hz. The region above the violet color is called the ultraviolet region and has a frequency equal to 7.9 into 10 to the power 14 to 3.4 into 10 to the power 16 Hz. The region below the red color is called the infrared region, and the frequency of the waves of this region is 3 into 10 to the power 11 to 3.9 into 10 to the power 14. Ultraviolet and infrared rays are not visible to the naked eye. Other important regions in the electromagnetic spectrum include radio waves with frequency less than 10 to the power 9 and microwaves with frequency of 10 to the power 9 to 10 to the power 11 Hz. Radio waves have the longest wavelength in the electromagnetic spectrum. Radio frequency region around 10 to the power 6 Hz is used for broadcasting. Microwave region around 10 to the power 10 is used for radar. Two other kinds of electromagnetic waves are X-rays and gamma rays. The wave nature of electromagnetic radiation successfully explains the phenomena of interference and diffraction. But the phenomenon of black body radiation, photoelectric effect, and the spectra of atoms were not explained. These things could be explained only if the radiation is assumed to be a stream of photons. That is, by considering particle nature. Let's understand these phenomena one by one. First, let us understand the phenomena of the black body radiation, which was given by Max Planck in 1900. In general, when radiation strikes any surface of the body, part of it is reflected, part of it is absorbed, and part of it is transmitted. For example, when an iron rod is heated, at first it turns red. As the temperature is further increased, it becomes yellow, then white, and finally turns blue. This actually shows that the radiation is emitted in the order of increasing frequency, red light being of lower frequency and blue light being of higher frequency of visible region. On the contrary, an ideal black body is a perfect absorber and emitter of radiation. A blackened metallic surface or a hollow sphere blackened inside with a small opening behaves almost as a black body. Any type of radiation that enters this small opening gets reflected multiple times within the sphere until all the energy is absorbed. Thus, a black body is not only a perfect absorber of radiant energy, but also a perfect radiator. Black body radiates the maximum amount of energy at a given temperature. Note that it radiates the same amount of energy it has absorbed. From the graph shown here, it is visible that at a given temperature, the intensity of radiation emitted increases with decrease in wavelength, reaches a maximum value at a particular wavelength, and then starts decreasing with further decrease in wavelength. We have seen that at a given temperature, there is a wavelength at which the maximum intensity of radiation is emitted. But the position of this maximum intensity shifts towards higher wavelengths with decrease in temperature. These observations could not be explained by the electromagnetic wave theory of light. To account for these experimental observations, Max Planck in 1900 proposed that radiant energy is emitted or absorbed discontinuously in the form of discrete packets or bundles of energy and not continuously. This is the first postulate of Planck's theory. Further, Planck called these discrete quantities or packets as quanta. Quantum is the smallest quantity of energy absorbed or emitted in the form of electromagnetic radiation. This means that the light radiations absorbed or emitted by atoms or molecules comprise a stream of quanta, but not continuous waves as shown. According to the second postulate, the amount of energy associated with the quantum of energy is proportional to the frequency of radiation. E is proportional to nu, or E equals h multiplied by nu, where E is the energy of the radiation, h is the Planck's constant 6.625 into 10 to the power of minus 34 joule/second, and nu is the frequency of radiation. To write this equation in terms of velocity and wavelength, substitute the equation 2 that nu is equal to c divided by lambda in the above equation. Hence, the resultant equation is E is equal to h multiplied by c divided by lambda. The third postulate says that the total amount of energy emitted or absorbed by a body will be a whole number multiple of quanta. That is, E is equal to nh nu. This means that an atom or molecule can absorb or emit either one quantum of energy or any whole number multiple of quanta. Note that only certain values of energy are permissible. This is called the quantization of energy. Now let us solve a numerical problem based on Planck's equation. Calculate the magnitude of the energy of 1 mole of photons of radiation whose frequency is 4.96 multiplied by 10 raised to the power of 14 per second. The first step involves writing the expression for the energy associated with one photon, that is, E equals h nu. In the second step, let us substitute the values of h, that is, 6.626 multiplied by 10 raised to the power of minus 34 joule/second, and the given value of frequency, that is 4.96 multiplied by 10 raised to the power of 14 per second. On substituting and solving, finally, we get 3.286 multiplied by 10 raised to the power of minus 19 joules. The third step involves writing the expression to calculate the energy associated with 1 mole of photons. That is, E equals nh nu. Here, n is equal to 1 mole, that is 6.023 multiplied by 10 raised to the power of 23. On substituting the value of n, h nu, in the equation and solving, we finally get E equals 19.788 multiplied by 10 raised to the power of 4 joule per mole, or 197.882 kilojoule per mole. In the previous module, we have learnt about the emission of radiation from a black body on the basis of particle nature. Now let us look at the photoelectric effect, which is also explained on the basis of particle nature. In 1887, Hertz performed an experiment in which he observed that when the surface of certain metals, such as cesium, potassium, sodium, rubidium, and so on, are exposed to a beam of light as shown, electrons were ejected. This is called the photoelectric effect. The electrons thus emitted are called photoelectrons. From this experiment, the following observations were made. 1. No electrons are ejected from a metal if the incident light has frequency of less than a certain minimum frequency value, called the threshold frequency. 2. The number of photoelectrons ejected is directly proportional to the intensity or brightness of the incident light. 3. The kinetic energy of the ejected electron is directly proportional to the frequency of the incident light. These observations could not be explained using the laws of classical physics, according to which the number of electrons ejected and kinetic energy associated with these electrons depend on the intensity of the light radiation. However, it is observed that the kinetic energy of the ejected electron depends upon the frequency of the incident light, but not on the intensity of the light radiation. For example, when the metal potassium is irradiated with high, intense red light having frequency of 4.3 to 4.6 multiplied by 10 raised to the power of 14 Hz for hours together, no electron is ejected. But as soon as it is irradiated with even less intense yellow light having frequency of 5.1 to 5.2 multiplied by 10 raised to the power of 14 Hz, photoelectrons are ejected. This is because the threshold frequency for potassium metal is 5.0 multiplied by 10 raised to the power of 14 Hz. Einstein explained these observations of the photoelectric effect, for which he received the Nobel Prize in 1921. He has taken into account the Planck's quantum theory of electromagnetic radiation for explaining the photoelectric effect. Note that the quanta were called photons by Einstein. According to Einstein, electrons in metals are held by attractive forces by the metal kernels, that is, the positive ions of the metal. To overcome these forces, the photons of incident light must possess a certain minimum energy, so as to release an electron from the metal surface. Thus, when a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron, and the electron is ejected without any time lag. From the quantum theory of radiation, we know that the energy of the incident photon is directly proportional to the frequency of the incident light. The minimum frequency that provides enough energy just to release an electron from the surface of a metal is called the threshold frequency, designated as nu-naught. Hence, when a beam of light, that is, a beam of photons, strikes the surface of the metal, electrons will be ejected only if the incident photons have the frequency nu greater than the threshold frequency nu-naught. Let us assume that the frequency of the photon of incident light nu is greater than the threshold frequency nu-naught. In other words, the striking photon has energy equal to h nu, and the minimum energy required to eject the electron is h nu 0. as the energy of the incident photon h nu is greater than h nu 0. The remaining energy, that is h nu minus h nu naught, is imparted as kinetic energy to the electron. Thus, h nu minus h nu naught is equal to half mv square. Here, m is the mass of an electron and v is the velocity of the ejected electron. On rearranging the equation, we get h nu is equal to h nu naught plus half mv square. H nu naught is constant for a particular metal and is designated as W naught, which is called work function. Now, the equation in terms of work function is as shown. Let us observe the values of work function for a few metals. Hence, if the energy possessed by the photon is high, the energy transferred to the electron is also high, and hence the kinetic energy of the ejected electrons is also high. In other words, greater is the frequency of the incident light, greater is the kinetic energy of the ejected electron as shown in this graph. Lastly, greater is the intensity of incident light or the number of photons that strike a metal, greater is the number of electrons ejected. For example, when more and less intense yellow light is made to shine on potassium metal separately, then relatively more number of electrons will be ejected from the potassium metal irradiated with high intense yellow light. Now let us solve a numerical problem based on photoelectric effect. Calculate the kinetic energy of an electron emitted from a surface of a metal when radiation of frequency 5.5 multiplied by 10 raised to the power of 17 per second hits the metal. The work function of a metal is 3.62 multiplied by 10 raised to the power of minus 12 ergs. The first step involves writing the given data as shown and then writing the appropriate equation to calculate the given problem. In the second step, let us substitute the values of h nu and W naught in the equation. On solving, we get the final answer as 3.63 multiplied by 10 raised to the power of minus 9 ergs. Hence, the electron will be emitted with a kinetic energy of 3.63 multiplied by 10 raised to the power of minus 9 ergs. Thus, these theories and conclusions, such as the black body radiation and the photoelectric effect, led to the development of further Bohr's model of atom. Bohr's model of atom could successfully explain the line spectrum of hydrogen atom that you will learn about in the next module. Before we begin to learn about atomic spectra, let's understand the term spectrum. When a ray of white light from the sun or an incandescent lamp is passed through a prism, it is dispersed into a continuous array of 7 colors, namely VIBGYOR. This is called spectrum. It is observed that in a spectrum, the radiation with lower wavelength bends more than the radiation with higher wavelength. That is why we see violet with lower wavelength at 400 nanometers and red with higher wavelength at 700 nanometers in the spectrum. The most common example of a spectrum visible to naked eye is a rainbow, consisting of 7 colors that constitute the white light. These colored bands merge into each other. Therefore, the spectrum of ordinary white light is called continuous spectrum. Electromagnetic radiations include a range of wavelengths, and this array of wavelengths is referred as the electromagnetic spectrum. When electromagnetic radiation interacts with matter, atoms, and molecules, they absorb some part of radiation and go to a higher unstable energy state called excited state. As the atoms are unstable in their excited states, they tend to revert to its original state, called the ground state, by emitting the same amount of energy that it had absorbed earlier. This energy can be emitted in a single step or in a number of steps. Depending on the amount of energy emitted, a radiation of particular wavelength is obtained. The spectrum of radiation emitted by an atom is called emission spectrum. In contrast to the continuous spectrum of white light, an emission spectrum is usually discontinuous with dark spaces between the bright lines. Such a spectrum is called line spectrum. The bright lines in the emission spectrum exist due to the fact that emitted radiations are only of specific wavelengths rather than a continuous spread of wavelengths as in the case of white light. A photographic negative of emission spectrum is the absorption spectrum. An absorption spectrum is recorded by passing a continuum of radiation through a sample which absorbs radiation of certain wavelengths. The missing wavelengths that correspond to the radiation absorbed by the matter leave dark spaces in the bright continuous spectrum. Unlike emission spectrum, absorption spectrum consists of a series of dark lines in the bright continuous spectrum. The study of emission or absorption spectra to determine the molecular structure is referred as spectroscopy. The emission spectra is also called atomic spectra, sometimes because each atom has a unique emission spectrum, just like each human being has unique fingerprints. The characteristic lines in atomic spectra can therefore be used in chemical analysis to identify unknown atoms. German chemist Robert Bunsen was one of the first investigators who used atomic spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by the spectroscopic method. The presence of helium was also detected in the Sun by means of the spectroscopic method. Now, let us study the line spectrum of hydrogen, which is a one-electron system. When an electric discharge is passed through hydrogen gas, hydrogen molecules dissociate to produce energetically excited hydrogen atoms. These excited atoms emit electromagnetic radiation of discrete frequencies while coming back to lower energy levels. The resultant hydrogen spectrum consists of multiple series of lines that are named after their discoverers. The first series in the hydrogen atomic spectrum, Balmer series, was discovered by Johann Jacob Balmer in 1885. Its lines belong to the visible spectrum of electromagnetic radiation. These are observed when the electrons jump from n greater than or equal to 3 to n equal to 2 principal energy level. Balmer showed that if spectral lines are expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey the formula wave number, nu bar equal to 1,09,677 multiplied by 1 divided by 2 square minus 1 divided by n square per centimeter. Here, n is an integer equal to 3, 4, 5, etc. Balmer's formula inspired the Swedish spectroscopist Johannes Rydberg to come up with a modified formula to describe all series of lines in the hydrogen spectrum. The equation may be written as wave number nu bar is equal to 1,09,677 multiplied by 1 divided by n1 square minus 1 divided by n2 square per centimeter. Here, n1 is equal to 1, 2, 3, etc. and n2 is equal to n1 plus 1, n1 plus 2, etc. The value 1,09,677 per centimeter is called the Rydberg constant for hydrogen. The first 5 series of lines that correspond to n1 equal to 1, 2, 3, 4 and 5 are known as Lyman, Balmer, Bastian, Brackett and Fund series respectively. Each of these series shown in the table represents the line spectrum emitted by the electrons of hydrogen atom when they change state from N2 to N1 principal energy levels. Here, N1 and N2 represents the lower and higher energy levels respectively.